Hello everyone, welcome to this video tutorial on how to use the Kiadam tool. My name is Julian and I will be your host in this video. Today we will generate a dataset from scratch to detect markers on an office table. Then we will train a model, YOLO V8, and we will measure how its performance is having been trained on the dataset we created in real images. So that we better understand what we are doing today, here are some images, example of the testing dataset. These are images of markers on a table that are sometimes accompanied by pencils. Then the objective will be to precisely detect the markers and not detect the pencils that accompany them. This is what we are going to try to aim for when created our dataset in Kiadam. First of all, we must navigate to the kiadam.com page, as it is written here, and it will present us with this home page. So what we need to press at the beginning is Start Free Trial. This will take us to the Kiadam tool, which will first ask us to do a sign up or login. If you already have an account created, we can put it here directly, but if not, you must press sign up. So I'm going to create a new account. And now we have the account created, and we can continue by pressing Get Started. So we are already inside the tool. Here we can see the home, which simply gives us quick links to the configurations of the dataset, which we will explain later. In the configurations view, we can see all our configurations. As it is a new account, we have no configurations yet, and we must create a new one. This is where we can see all the datasets that we have created. Again, we have none generated so far, therefore it says there aren't any yet. We have also two other links here in the left sidebar, which are the resources link first. Pressing it takes us to the Kiadam blog, and we can see some articles on how to use the tool. And below, we can see a link to support that simply opens the Kiadam Discord. Let's start by making a configuration. That is, by pressing the New button. We choose a name for the configuration. In this case, it will be markers. This is the initial screen for creating a configuration. Let's go through the settings one by one. First of all, here we have what is the image size of each of the images of the generated dataset. In this case, we will ask for 640 by 640, but there are other options if you want to use something else. Here we have the number of images that will be generated. In this case, 100 images are being generated, but we will increase the size to 300. Regarding the size of objects relative to the final image, this is how much percentage of the image each object that we position will occupy. It's between 30 and 70% of the image for each object, but we'll change it to have between 10 and 90% of the image. Regarding the number of objects in the final image, that corresponds to how many objects will we put on the background. In this case, it is between 1 and 8, and we will leave it at that. The percentage of background only refers to how many images in our dataset will not have objects, but will only have the background. And in this case, we will leave it at 5% as it is by default. For the OOD percentage, this corresponds to how many objects will be added of which one does not want to recognize. If we take the example of the previous image we had seen, an OOD object would be the pencil, an object that is in distribution or IID would be the marker. Finally, this last setting in the general settings corresponds to the split between training, validation, and testing. In this case, we are choosing to have validation and 80% training, 10% validation, and 10% testing. Let's note that this is a double slider and that you can easily choose all the percentages so that they add up to 100. But we will leave it as it was by default. And since we have already chosen the initial settings, we will press Save at the top of the screen. This will save our configuration. Now let's continue on the second part about label objects. Here, what we will do is add some images of objects that we want to recognize. In this case, the markers. Let's see what these objects correspond to. Here are some examples of objects that could be used to recognize markers. Let's note that these objects correspond only to the marker. They have nothing in the background. This is achieved thanks to a technique called segmentation. It detects exactly where there is an object and where there is not, and thanks to that we can remove the background easily. If you're thinking about whether we'll see this in this video, no, we will do it in another video, because it goes outside the scope of what we are going to see today. So, first we'll add those objects. The app may take a while to upload images, so we'll come back when they are all uploaded. All marker images have already been uploaded. Now, what we want to add is a label to each of one of them. Then, to each marker, we will put a label that says marker. We could edit each of the images separately. What we will do is press the Go to Labeling button, and that will allow us to label all the images of objects, one after another, that do not have any labels. Note that we can also use the down arrows on the keyboard to select the options that we already are using in another object and enter to enter the option to facilitate labeling. In this case, we will use the same label for all markers, since we will not distinguish the color. So now we have all the marker objects that we are going to use in this tutorial labeled. However, they are not the only objects that we will add to the application. Now we will add some objects so that our model learns not to detect pencils. If you remember well the images we had, they had pencils as well as markers. So, something we can do to help the detection of the markers and avoid the detection of the pencils is to add pencils so that the model learns not to detect them. For that purpose, we will use other objects that are also already segmented, like this here. So, we will upload these objects to the application. And we will wait for each one of them to upload. All have been uploaded, and now we will click the Go to Labeling button for a second time. However, now we don't want to put labels anymore, since we don't want anyone to be detected as an object. Therefore, we will click the Has no label checkbox. We'll do this with all the objects we just added. And this, as you can see, leaves the markers with a label, which is precisely the marker, and all the pencils without a label, since we will not put any bounding boxes around them. Returning to the previous settings, we will have 90% of all objects in all images corresponding to markers, which will have their own bounding box and label, and 10% of pencils, which will not have any bounding box or labels. We will press save since we have already finished this part. One question you may have is about the bounding box. Do you have to create it manually, or is it not necessary to create it? Precisely, Kiadam ensures that the user has to do the least amount of work possible to have their dataset created. Therefore, when uploading these markers, Kiadam automatically assigns them a bounding box by positioning them within the generated image. So, the next thing we're going to do is to choose the background images. Precisely, how do we create our synthetically generated image with Kiadam? We choose a background image, and then over it we put some of the objects that we had chosen previously. We need to choose backgrounds that correspond, that make sense within the context in which we will detect in production. In our case, if we see the images we had, generally we have wooden backgrounds. In fact, we have only backgrounds consisting in wooden tables. So, for the background images, we will choose images of a wooden table. Here we can see some of the images that we will use as backgrounds. To upload these images, we will come here, add images, and in the same way that we uploaded the markers and pencils in the previous part, we will choose here the background images that we want to upload. This may also take a while to upload all the background images, so we'll wait a few seconds. You can see that in the background images there is a button with the crop symbol. This button is a button that is used when we want to crop the image. You can not only crop the backgrounds, but also the objects that you have uploaded. If this background has elements that I do not want to appear in my final image, I simply create here the portion that I want to keep and press crop, and this adds a new image that only corresponds to the small part of the background that we wanted to keep. In this case, we won't keep it because we don't want it, but there might be a case in which we want to save it. Since the background images are already uploaded, we'll press ready, and then we are going to save. Now we have uploaded the background images that we are going to use to generate our synthetic dataset. Still, we have more options to choose background images from. We can choose if we want in some of the images to put a noise background, as it shows here. Instead of the wooden table images, we can put this, which is random pixels. Also, if we want, we can choose that some of the images have a background consisting of a single color, random 2. We are not going to choose these two options since they don't help us in this case. Now we move on to the most important part of the entire generation, which is the transformations. This is the core of Kiadam. These are the transformations that data augmentation will make to the different parts that make up the image. The first are the transformations that will be applied only to the images of the objects, that is, to the markers, when we position them on the image. To look what transformations can be applied, there are several, but we will focus on the geometry ones first, which in this case will be changing the perspective, rotating the image, or doing a flip. We also can make the markers look a different color, that is, change it a little greener, a little redder, change the contrast of each marker, give it a bluer. In this case, we will only choose the skew and rotate ones, and the rotation will be edited to affect all the images, and so that the angle is from minus 180 to 180. That is a complete rotation. We don't care what orientation we have because the markers could come in any orientation. Let's go to the skew editing dialog for a second. It is not necessary to set confirm for the skew transformation because we have not edited it and it has the default values. But when we go to the rotate transformation, we may see that the changes are not saved. This is because we forgot to press confirm. When closing the box, you should press confirm, because if you don't, the changes will not be saved. So, as I said now, for background images, the transformations are quite similar, except that you cannot rotate, you cannot skew, but we can choose different colors, different brightness, blur, among others. In this case, for the background images, we will not choose any transformations. Then, when we have the image with the background and the markers pasted on top, we can choose transformations for the entire image, which are the composite image ones. What we will do here is choose some to make the images vary a little from one to each other. We'll choose color distortion, brightness, contrast, and blur. And we will leave it with the default values, which are the ones indicated here. Now we will save. And this is the configuration that we will use to generate our dataset. Now, to generate the dataset, we will press the Go to Datasets button. And we will click Generate First Dataset, which will begin the generation. It can also be done from the Generate button above. The process of generating a dataset takes a while, since all the images specified in the configuration must be generated. So this can take 5 minutes sometimes, depending on the number of images and the complexity of the transformation used. So we'll see you in a second. The generation is already ending, so soon we will be able to download our dataset of generated images. But first, as soon as we finish generating, let's review the images we generated. So when it says 300 over 300, now it says it's completed, which means all the images have been generated. Let's click on the dataset to see it in more detail. So here we can see the images that our tool generated. We can see that in the background we have the images of the table that we were using, and then the markers are pasted on top. And the transformation that we decided to apply are applied. For example, the markers are not always facing up, but are rotating in a random rotation. And also, sometimes the complete image is with a changed color or blurred, although here I think there is no blur, but in some of the pages it may be shown. And we can see that there are 38 pages corresponding to the 300 images we just generated. Also, by clicking on any of the images, or down here in View Image, we can see that the image and the markers are displayed along with their bounding boxes. Here we can see that the pencil does not have a bounding box, and this is precisely because we decided that it did not have a bounding box, but saying that it didn't have a label. This is for, repeating what I said before, to train the model not to recognize pencils as markers. Having seen the images and being satisfied with their generation, we will press the Generate Zip button. This will take all the images and compress them in the cloud in a YOLO V8 format. That is, by downloading this, the format to train a YOLO V8 model will be ready. In more detail, what we will do is generate the train, test, and val folders, and inside each one there will be the image and bounding boxes corresponding to each of the images that had been generated, and separated according to the split that we set in the configuration on the previous screen. In this case, there are 80% training images, 10% validation, and 10% testing. The process of generating the zip also takes a while. Therefore, we will wait for it to finish and then we will return. And the zip is generated in the cloud. Therefore, now we will press the download button and this will download the zip to our computer. We open the zip to check its contents. Let's see first that we have the data.yaml file, which specifies which classes we are going to use. Then there is the number of classes and the folders where is each of the split images are located. Then here are the folders corresponding to train, test and val under images, we can see here that we have the images, as we can see here, and in labels, what are the bounding boxes associated with each of the images of the generated dataset. So we can see that we have class 0 that corresponds to marker, and here are the coordinates of the bounding box. So now that we have our dataset downloaded, we are going to create a new Google Colab. We are going to name it Markers. This is where we will train our YOLO V8 model. So first of all, what we will do is to upload the dataset that we just downloaded. For this, we are going to press the Upload to Session Storage button, and we are going to choose the dataset that we just downloaded. It may take a while to upload, but we will wait patiently. To do the training, you must use a GPU instead of a CPU. This is because the CPU is much slower. To do that, we have to come to runtime, change runtime type, and choose the T4 GPU, or one of the better ones if it is enabled for your Colab account. And we choose save, and this will automatically change the runtime type to GPU. Apparently, changing the runtime type deleted the uploaded file, so we'll upload it again. It is also important to know where the images we are uploading are saved. These images are being saved in the Colab runtime space that is assigned when we connect to a runtime, in this case the T4 GPU. Therefore, when we close the Colab, the images will disappear. The important thing is, at the end of the training, to download the model if we are interested in conserving it, or connect to Drive and save it there. But we are not interested in keeping the dataset in the cloud. Therefore, we will just upload it in the session. What we are really interested in is the trained model. And having uploaded the dataset in zip version, what we will do now is first to decompress it according to the folder structure that is in the same zip. We will do it with this command: unzip, then we enter the name of the file we want to unzip, and -d, and the directory where we want to unzip it. That is, this will create a folder called markers1. To check the name of the zip file, you must see it in the sidebar. Here it is, Markers version 1. Here's the name of the zip file, and here we write it, and then the directory when we want it decompressed. And to view it, you must press this button which says reload, and there the Markers1 folder will appear with the folder structure we saw in the zip. We have it unzipped, and we can use it directly instead of, well, so now it's unzipped. We'll install the requirements for training YOLO V8. The requirements for training the YOLO models are just ultralytics. And you may wonder, where do we get these requirements from? Ultralytics is the company that is responsible for maintaining the YOLO models. In this case, well, YOLO v3 up to YOLO v8. And they have provided a pip package, which is Ultralytics, where you can easily train and validate many of the models that they deliver. In other words, these commands simply go to Ultralytics page and you can obtain this pip install Ultralytics commands and the instructions to then train the model. If you want more details on how to train and how to do the different operations on the models that Ultralytics offers, you can easily go to the Ultralytics page and review the documentation on how to train. So we will install the Ultralytics requirements. And just like that, we have everything that we need to train. Now we will make a small change in the data.yaml that we have here, since it shows us here a path that does not totally correspond to the path that we have here in our collab. We need to make it so that it's an absolute path and it leads directly here where it says images in each one of the train, test, and val folders. Therefore, we will copy a little code, and what it will do is, instead of having this path here, change it to the absolute path. In this case, a path that leads from the runtime root to the images folder. We'll review what this code is now. First, we import YAML, which is the library necessary to make changes to the YAML files. Then we load the file into a dictionary, keep everything except the path, which we change to content/markers1, and then we leave train val like what it says here. And then we create a file again, renaming it data.v8.yaml with the new configuration, which is what we will use to train the model. If you want to see the code and all the Google Colabs we used in this training, you can go to the Kiadam.com page and see the article we have published. More on this later. So now we will start with training the model. First, we will import the YOLO object from Ultralytics, the YOLO class, and this is the class that will allow us to load and train the new model. Next, we will load the pre-trained weights from YOLO v8s.pt. They are also available in YOLO v8 or Nano, which is the smallest of all, YOLO v8m, and YOLO v8x, which is the largest so far. Then, having loaded the weights, we will start training. and we will pass these different parameters. First, in data, we pass the path to the YAML that we just created, which is data.v8.yaml, and with that we can train easily the model. We will pass the image size, which is 640 times 640, as defined in the configuration. The number of epochs will remain at 100, since 100 epochs is enough to achieve results within the model validation. We will pass 16 as batch size. That is, 16 images will be read at a time, and this number is enough. Actually, this, when trying, was what worked best, since setting a slightly larger batch size sometimes results in Google Colab's RAM running out, because it can not process so much data at once. It is also important to have a batch size that is not so small, so that the model generalizes better. Finally, we will leave a name for the trained model, which will be Marcus1, so it will be saved with this name inside the Ultralytics model folder. So now we'll run this command and see what happens. We can see that the YOLO V8 pre-trained weights are loaded first, and then we start training. The beginning of training is seen because the epochs begin to appear, and the progress of each epoch. So we are in the epoch 1 out of 100. We can see how much memory is used and the progress of the epoch. At the end of each epoch, we can see a summary of how the precision, recall, map 50 and map 5095 are in that epoch. We are interested in this being as large as possible. Therefore, we expect them to be above 0.9 in the case of recall and precision. This process also takes a while, so when you're finishing, we'll come back. The training of the model is already finishing. We are epoch 94 out of 100, and we can see we are having pretty good metrics in the validation set. Here we can see that in the validation set we have 0.989 in precision, 1 in recall, 0.994 in map 50, and 0.914 in map 5095. This is how the model performs within the synthetic datasets. But now we also want to know how the model performs within a dataset that is from the real world. Therefore, when this is completed, this is what we will do. To check now how the model behaves with a real life dataset, what we do is to take a set of images on a wooden table with markers and pencils, such as those shown previously, and from that we have created a YOLO V8 style dataset with the images and the bounding boxes on which we can test our model. We can immediately review the images that we are going to measure on. And in this, we can review some of the images. You may wonder whether we used these images to train the model. And the answer is no, of course, because the images we train with are synthetic images, and the images we have here are real images taken with a camera. The model has never seen these images. So what we'll do is, just like in the other one, to upload the zip so we can use it in the cloud. So this is this one here, and it will take less time to upload than the other one because there are less images. There are 100 images and the other were 300. When it is uploaded, what we will do is to unzip with the same command, only now we will change the input zip and the output directory. The zip is called penSimpleTest, and we will call the directory the same, penSimpleTest. We got an error now, which is an error that can sometimes appear after having trained with YOLO, which is precisely that the locale is not what is expected. And UTF-8 is expected, and we have ANSI X34. To correct this error, what we will do is to add a new command. I would like to have the default encoding of our collab is UTF-8 with this command, which is import locale, and then locale.getPreferred encoding is lambda UTF-8. And having done that, we can easily decompress our dataset without problems. And we can also see it here on the left, having reloaded the files. Here it is, our already unzipped folder. Now, what we have to do is make the same change that we made with the first dataset with the YAML, so it correctly detects the folders. Then we load the YAML. Again, we change the path to be the absolute path, and then we save it. Finally, it remains to validate the model with a real-world test set. Basically, what we do is to first load the model that will be in the location of runs, detect markers 1, which is what we call the model, then weights, and best.pt. And we will validate it with the dataset that we just put, which is datav8.yaml in penSimpleTest. We run this cell, and it will give us the metrics in real-world images. And as you can see, we are achieving metrics above 0.95 precision, recall, and map 50. Therefore, we can say that our model was well trained and with a dataset that is used to detect images of that type. If we go here to runs, detect val, which is the name in which the validation was saved, in this case the testing, we can see many images that correspond to metrics of the model. We can see, for example, the F1 curve. We can also see the P curve, the R curve. We can see the confusion matrix. Here, as we can see, 184 times it detects markers correctly. Let's make it a little bigger, so it's easier to see. I hope it looks better there. We can see 184 times it detected markers correctly. Only 26 times it detected the background as if it were a marker. Only 4 times it detected a marker as if it were a background. That is, it did not detect it. We can also see other images. In this case, there are no metrics, but there are some examples of images and their predictions. For example, we can see here that although it sometimes gets confused, it generally detects the markers well. We can see that all the boundary boxes in this case, in these images, are well placed. Let's check again what the final metrics obtained are for precision, recall, and map. The latest metrics are here, and we can see that the precision is of 0.968, the recall of 0.955, the map 50 of 981, and the map 5095 of 745. To see the article, you can go to Kiadam.com, go to blog Kiadam in action, and then click in this one here. Part 2 of Increase Model Robustness against Out-of-Distribution Objects with Data Augmentation. When you open it, it is a little more in detail what we did today. The collapse, in fact it is a single collab, is here. And you can even use this collab to train other of the models using Kiadam if you want. Well, this was the tutorial on how to start a dataset from scratch and train a V8 model with the generated dataset and measure its performance on a real-world dataset. Thank you very much for watching.